2.3 limit laws. The following limit laws that I'm going to present to you are on page 77, but if you like to hear me talk, then here we go. First, we're given the statement, if the limit of f of x as x approaches c and the limit of g of x as x approaches c exists. So let's talk about this for a minute. They both have to be approaching the same c, and both limits have to exist. So for example, if f of x was approaching infinity, then this wouldn't be true. And we're going to see in the sections ahead why that is. Okay, so number one, we have the sum law, which is that if we have the limit as x approaches c of f of x plus g of x, then we can distribute that limit through. So we have the limit of f of x as x approaches c plus the limit of g of x as x approaches c. Next, constant multiples. So if we have a constant k, then what we can do is if we have limit k f of x as x goes to c, we can pull that k out and then take the limit of f of x as x approaches c. So a quick example of that one is that if we had that the limit of f of x as x approached c, let's say that this was given, let's say they told us that this was 5. Then we were asked to find the limit of 3 f of x as x approaches c. Then we can pull this 3 out, so that would turn into 3 times the limit of f of x as x approaches c. And we know that this is 5, so that's going to become 3 times 5, which is 15. All right, moving on. We have the product rule. This is a super powerful rule. It states that limit as x approaches c of f of x times g of x equals the limit of f of x as x approaches c times the limit of g of x as x approaches c. That's why it's so important that these two limits exist. Now, we have the quotient rule that if the limit of g of x does not equal 0 as x approaches c, then the limit of x approaches c of f of x over g of x equals the limit of f of x as x approaches c over the limit g of x as x approaches c. Remember that dividing by 0 is bad, and that's why we have this prerequisite on g of x that it can't equal 0. Okay, now we have some cool power and roots rules. So if we let p and q be integers, that means whole numbers, so like 1, -1, 4, etc. And we let q not equal 0, because remember, dividing by 0 is bad. Then the limit as x approaches c of f of x raised to the p over q is the same as if you took the limit first and then applied p over q. We'll be looking at some of those in just a minute. All right, and so it follows that if we take the limit of x to p over q as x approaches c, then that's going to equal c to the p over q. All right, so let's do some examples, guys. I'm so excited right now. Okay. So let's do the limit x to the 4th as x approaches 2. Now, by the very last rule that we just got, this is going to equal 2 to the 4th, which is going to equal 16. Oh, look how easy that was. We didn't have to graph anything or make any tables. These rules are amazing. Okay. Next, the limit of 4x plus 1 times 6x minus 1 as x approaches 1. Now, I can break this up into the limit of 4x plus 1 as x approaches 1 times the limit of 6x minus 1 as x approaches 1. Now, I know that these both are continuous functions, so what I can do is I can just plug 1 into both. So this would become 4 times 1 plus 1 times 6 times 1 plus 1. Okay, so that'd be 5 times, whoops, that's not plus, that's minus. 5 times 5, so that's 25. Okay, on to the next one. Now what I can do is that I can split each of these up. So that would be the limit x squared as x approaches negative 3 plus the limit x as x approaches negative 3 plus the limit 15 as x approaches negative 3. I could have split these equations inside of here up the same way. So the limit of x squared, this is a continuous function, so I can just plug negative 3 in, plus x is also a continuous function, so I can plug negative 3 in. Now 15 is a constant function, so no matter what x is, this is always going to be 15. So I'm going to have 9 plus negative 3 is 6 plus 15 gives me 21. Okay, now we're going to solve the following given that the limit of f of x as x approaches 4 is 3 and the limit of g of x as x approaches 4 is 1. So we can evaluate the limit as x approaches 4 of f of x over g of x because g of x is not 0. It's 1, so that's going to equal the limit of f of x as x approaches 4 over the limit of g of x as x approaches 4. It's going to be 3 over 1. 3 because it's given, 1 because it's given, and that will equal 3. Okay, I'm going to write this one in a different color. It's getting a little crowded up here. All right, so for this next one, we have the limit of f of x squared times g of x. Now, I can square this guy by the power rule. So this is going to become the limit of f of x as x approaches 4 squared times the limit of g of x as x approaches 4. So I'm using the power rule here, and then here I'm using the product rule. So this is going to be 3 squared times 1, which is going to give me 9. Okay, last but not least, I have the limit of g of x over x squared. Oh, I got a new function here. I'm feeling kind of weird. As x approaches 4. Well, this guy in the bottom, as x approaches 4, let's look at that limit first. So I'll draw a star here. This is kind of our scratch work. The limit of x squared as x approaches 4. Well, I know this is a continuous function, and not only do I know that, but I also have a rule at the bottom of my limit laws that this guy just equals 4 squared, which equals 16. Well, since this guy doesn't equal 0, I can invoke the quotient rule, and I have that the limit of g of x as x approaches 4 divided by limit of x squared as x approaches 4, which equals 1 over, and I just said this guy equaled 16. So these rules are very powerful, but you have to make sure that you are using all of the prerequisites of the limit laws. So for example, in each one of these that we did, we made sure that f of x and g of x both existed. And when we were doing the quotient rules, we made sure that g of x, or whatever function was on the bottom, wasn't 0. So these are important things that you need to check, and also wouldn't hurt to note down when you're solving a problem.